picture just after the present talk. So the first speaker of the afternoon is Pedro Salomão from Sao Paulo, and he will talk about Hénon-Heiles dynamics.
So thank you very much for the invitation. In this talk, I will say something about this Hénon-Heiles dynamical systems, and I'll try to explain how we can use these results from symplectic dynamics to prove something about the system. Okay, so let me say a bit of the history of this dynamical system. It was proposed by Michel Hénon and Carl Heiles in 1964 in this paper. It was a system with 2 degrees of freedom, which describes the dynamics of a star inside a galaxy. And they did some numerical experiments to prove, or at least to have some evidences that that system had no other integrals of motion. They were discussing the possibility of the system to be integral, but they could do good numerics at that time to at least to show or to have a very good evidence that this system is not integral. So to explain a little bit about the definition of the system, suppose that we have a galaxy, and it's assumed that it's centrally symmetric, okay, the distribution of mass, and it produces a potential, okay? And there is a star which moves according to this potential, meaning that the acceleration of the star is minus the gradient of the potential function, okay? And it's assumed to have these axes of symmetry. So with this symmetry, it's possible to reduce the study of this 3 degrees of freedom dynamical system to 2 degrees of freedom dynamical systems. For instance, you can take a plane which contains that axis of symmetry, and so you can find a potential on that plane, so that and then you study this dynamical system on the plane, this potential system on the plane, and then because it preserves the angular momentum, you can recover the original orbit by studying this 2 degree of freedom dynamical system. Okay? And the question that they were trying to answer, so you have the total energy that is preserved by the flow, you have the angular momentum. Is there something else that we didn't find, or there is nothing else? So the system is the following. We have this Hamiltonian. Now it's a potential on a plane, and it's given by this very simple expression here. So the kinetic part and plus the potential part. The potential part is taken to be a polynomial with degree 3. And the equations of motion of the star would be this one. It's very simple, okay? So it's a very, very simple system. Sometimes we could see some parameters here in this potential part, but the original potential was taken this one here, okay? So what can we say about this very simple system? First, I think it's important to mention that there are a lot of symmetries in that system. For instance, of course, it preserves the total energy. The flow preserves the total energy. And it has the symmetry of x1 here. So let's say that we are on a plane. And we have a solution here. So the reflection is also a solution. About this x2, the x is x2. This one symmetry. The other symmetry is the reversibility, because, for instance, suppose that we fix the energy and we project the energy level to the x1, x2 plane. This is the Hill region. Let's say that this is the projection of the energy level to the plane. And so let's say it's a disk This is what's going to happen in the case that we study the system here. And there is the interior. The boundary is called the zero velocity curve. And in the interior, if you want to study the flow projected in the interior, it's like studying the geodesic flow of the Riemannian metric given by this expression here, which depends on the total energy that you fix and the potential function. So this conformal metric here. So it's just like studying a geodesic flow on that region there. And in particular, it's reversible. Like if you have a solution which goes this way, then in the opposite way, it's also a solution. Okay? Just because it's a kinetic plus potential. The Hamiltonian has this form here. Okay? This is another symmetry that's part of the Hénon-Heiles dynamics. And the other one, which is also interesting, is that it has this Z3 action, which acts on these two factors, the X factor and the Y factor. Okay? So the Hamiltonian is invariant by this transformation here. So whenever we see a solution here, we can rotate by 2 pi over 3. It's still a solution. Okay? So I think these are the main symmetries that we see directly from the equations that we can use. Okay? So let me say something about the Hills region of this system. So the Hills region is the projection of the energy level to the x1, x2 plane. So it coincides with the region fixing an energy, the points where the potential is less or equal than the energy. Okay? And we have the following situation. So for negative energies, the Hills region is like, it has 3 unbounded components here. Okay? And the dynamics is very simple in this case because the solutions come from infinity and go back to infinity. There's nothing really interesting to understand the dynamics in this case. For negative energy, nothing really happens here. So this is for negative energy. When energy is equal to 0, it's a critical value of the Hamiltonian function. So the origin is a critical point, so it's a rest point. The only difference is that now you have this rest point at the origin if the energy is equal to 0. Okay? So it's essentially the same, it's a critical value. There is a second critical value at 1 over 6. And so we study now what happens when you are in between. So this critical point, this rest point of the flow is a minimum, a local minimum of the Hamiltonian, of the potential. Okay? So when we increase a little bit the energy, so energy in between 0 and 1 over 6, we have a component of the energy level, which is diffeomorphic to the trisphere, which projects there onto a disk that we see there, this component here. And here the dynamics is interesting. Like, as before, the same happens in these 3 unbounded components, that it still exists. But the dynamics here is very interesting. It's like the star is moving. The star does not escape from the galaxy. Okay? But still very complicated dynamics there. So now increasing, what happens when we increase the energy until 1 over 6, that small region there, it increases, and then it touches the unbounded components. At 1 over 6 is a critical value of the potential. So we have these 3 points where that bounded region touches the unbounded one, unbounded components, like in this picture here. Maybe it's not so clear, but so here in this corner here, and here we have 3 critical points of saddle type. This is a rest point of the flow. And the dynamics, again, outside here is uninteresting. And here is a bit more complicated. I'll say something about this. Okay? So this is a saddle point. It's what's called, it's the point in that energy level which projects here is a saddle center equilibrium point of the flow, meaning that it has a pair of purely imaginary eigenvalues, the linearization of the vector field, and also a pair of real, with opposite signs, real eigenvalues. Okay? And so it has like a two-dimensional part, which is hyperbolic, and a two-dimensional part, which is a center. So what happens when we go a little bit above 1/6 is that there is a connected sum of the energy levels. Okay? And now dynamics is also interesting because you could have trajectories which enters through this region here and then escapes from this other region here, or all sorts of combinations here. So there is a lot of symbolic structure in this dynamics. So we could have trajectories which stay bounded, but we could still have trajectories which they go to infinity, and they change the components where they enter and they exit. Okay. So I will try to explain a little bit more of the dynamics in this situation and in this other situation in the bounded component here. So let me explain a little bit the dynamics in this bounded component here. Oh. Here, okay? So it's well known that in this region here there are 8 periodic orbits, special periodic orbits, and this is a true picture. It's like it's the real flow. It's not just a scheme. And we see here that we have 3 green orbits here, which are straight lines here. Because of that symmetry, of course, that symmetry of rotating is just, you have one orbit, one of the green orbits, like, let's say, in this region. So the orbit oscillates here on a straight line. Here. So this is the only point where it has 0 velocity, so it goes down. This is the periodic orbit. And then you have the other 3. This one is very simple to obtain because you can solve directly the equations, like just go there and find it. Very easy, because this line is invariant. Okay, so it's very easy. And then you can rotate to produce these other 2 orbits here. Okay. Because of that symmetry that I said in the beginning. Okay. Then we see that there are these 3 other orbits which are red. And it's not so easy to obtain, but it's not so difficult. The idea is the following: to prove that they exist, there is a shooting argument, which is the following. Suppose that we start. So this is, let's say, this is pi 3. This one here. This is pi 1. And this is pi 2. Okay? So when we start, so there is, what is possible to see from the equations is that all the solutions here, which stay here in this region, they are attracted by this line here. Okay? I mean, the acceleration of the solution has a positive component towards this line here. So if you start here, you see that it gets closer to this, and it intersects this line on an acute angle here. And if we move the starting point along this curve here, we see that it will intersect this line with an obtuse angle here. So there is a point in between here, and we see there that it will reach this line in a perpendicular way. So then you can reflect because of the symmetry. Maybe it's not so symmetric here, but should be. So, and you can reflect and continue. So it will reach this point, and then it will go back. Okay, that's how we obtain this periodic orbit. So it's a shooting argument, just interpolating different behaviors here. Okay, and then by symmetry we could rotate to produce the other three. Okay. And finally, there are two other periodic orbits which project on that simple closed curve. It's pi7 and pi8 in both directions. These are two other periodic orbits, and the argument is very simple. It's very similar to that one, in fact, to produce this orbit. We start with solutions which leave this line perpendicularly. Okay? And if you start very close to this point, the solution will hit this line with an obtuse angle here. And then if you vary along this line and take something which is very close to this point here, it will hit this line in an acute angle. So there is something in between, which, let me try to, which will live here perpendicularly and will hit this line in also perpendicularly. And then, because of those symmetries that I said in the beginning, you can reflect this by rotating 2 pi over 3. And first you reflect with respect to this axis here, and you produce this other part here. And then you can rotate by 2 pi over 3 to produce the remaining parts of this orbit here. Okay. Okay, this is how, and then in this case, it's this orbit that you obtain. You can, by the reversibility, you have this other one. And an interesting fact is that this orbit is symmetric, meaning that if you rotate this, if you act by rotating, using that Z3 action, it's invariant. This orbit is invariant. So another fact that maybe it's interesting to mention here, because later we will somehow be interested in this property of being hyperbolic or elliptic, is the fact that so these orbits here that I said in the beginning, they might be elliptic or hyperbolic. Depends on the value of the energy. And it's interesting, when you go to the energy, to the critical value, it oscillates in between elliptic and hyperbolic infinitely many times. So you have this infinite change of stability of this orbit as you go to the critical value, 1 over 6. Okay? The red orbit is believed to be hyperbolic for most of the parameters in between 0 and 1 over 6, this one, hyperbolic. And this one, it's believed, well, not to be elliptic for low energies, but then at some point it becomes hyperbolic, this one. And for those who are interested in indices, this orbit here, the index goes to infinity, because the limit, this orbit, the index, when you increase the energy, goes to infinity. The index of this orbit seems to be 3 or 4, depending on whether it's elliptic or hyperbolic. And this one I haven't computed. Maybe this one is, yeah, it could be 3 or 4 also. So there is this survey by Churchill, Pecelli, and Hod, which say much more about these orbits here. But let me say the first object that to study the dynamics of this system is to see that with that property that I said that, for instance, again, by the symmetry, the orbits are attracted by this line here. The acceleration has a positive component to this. So any solution here will be oscillating from one side to the other infinitely many times. So this orbit here, it determines a global surface of section. For instance, if you take all vectors along along this orbit, I mean along this projection which points to the right, then it's for that energy. So it determines a global surface of section. Any solution will start with a given vector here, and it will eventually return to another vector. Okay? So it's a global surface of section for the flow. And we can plot some numerical to see the behavior and to have an idea of what's happening. So for low energy, it's not so low, because 0.1 is not so low. If you take very low energies, then it's close to the linear system. So it looks like integrable. But if we increase a little bit, then we start to see this chaotic behavior here. Of course, this orbit here that we see, it's elliptic. It corresponds to the blue one, the one here, and here. There's 2 points here. I mean, in the opposite directions. And we see the other hyperbolic orbits. Here there is a hyperbolic orbit, one here, and another here. This corresponds to the 3 red orbits. And then we also see other elliptic orbits which will correspond to these other 2 here. So if we increase a little bit more the energy, slightly below the critical value, then we see this, what they, in that paper they call ergodic. It's not ergodic, but they call it. And so here, so in this region here that we see a lot of points, it corresponds just to 3 or 4 different trajectories. And it spreads over that region here. And this, we see 2 small regions here. It is this blue orbit which bifurcates. It used to be elliptic, then it becomes hyperbolic in the middle here that we don't see, but then there will be a period 2 elliptic orbits nearby. And then at the critical value here, so this periodic orbit, it becomes a homoclinic to that critical point, to this equilibrium point of the flow. Okay, it converges to the boundary, which is the boundary of the global surface of section that we see there. It becomes a homoclinic to the equilibrium point. Okay, this corresponds to the equilibrium point, the singularity here, and this orbit is just a homoclinic to this point. Okay, and then the flow becomes more and more chaotic. And then when you go slightly above that value, then of course, then we don't have a global surface of section anymore, because the orbits might escape in finite time, so it doesn't make sense to talk about global surface of section. Okay. But there is this observation, which was a computation by Schneider last year. He checked that, so the previous component, without disconnected some stuff, so without this, the energy level is a 3-sphere. It's an embedded 3-sphere in R4, okay? And it projects in this region here. And this embedded three-sphere is strictly convex. Well, it's a simple computation, but with this fact, we can use to say much more about the flow on that energy level than just simply finding these orbits. It's known that there are infinitely many periodic orbits, this type of stuff, but we can say a lot more with this simple fact that this is strictly convex. Okay? In particular, the energy level is dynamically convex, meaning that the index of every periodic orbit is at least 3, the Kohn-Lisender index. And what else? And we can even, with that Z3 symmetry, we can take the quotient of the energy level. It has this Z3 symmetry, so to obtain a length space. And this length space is L31 or L32 with opposite contact structures. And then we can use results for length spaces, for Hebb flows on length spaces to apply to this to this energy level with this quotient. Okay. In particular, it's possible to obtain this rational disk-like global surface of section. So one result that it's possible to apply using this fact that it's dynamically convex is a result with Riniewicz, which says that if we have suppose that we have a dynamically convex contact form on the length space L32 with the standard contact structure, and if we have a P, if P is 3 unknotted closed Hebb orbit with there is this invariant which depends on the contact structure, which is the rational self-linking number, which is 1/3. Then this periodic orbit, which is just a Hopf fiber projecting to this a 3-to-1 to a periodic orbit on the length space. Then it's the boundary of a rational global surface of section, okay, on the length space. So in this case, this orbit that I put here in blue, it's symmetric, so it projects down to this 3 unknotted self-linking -1/3, and so it's the boundary of a rational global surface of section. Okay. It's an application of this result. And what else I can say? It's okay. So this result here that we see, it assumes the existence of this P unknotted periodic orbit with self-linking number -1/3. And but there is a conjecture. So one of the questions is, if you give a dynamically convex contact form on a length space, if there is this orbit with similar properties. In the case of L32, if there is a 3 unknotted closed Hebb orbit with the rational self-linking number -1/3 and index in a set being 3, 4, or 5. So this conjecture is based on the result by Schneider, which says, well, in fact, the first result was given by Hofer, Vysotsky, and Zender, that if you give a dynamically convex contact form on the three-sphere with the standard contact structure, then you have this unknotted periodic orbit self-linking -1, which is the boundary of a global surface of section. Then that result that I mentioned before, no, it's not this one. Then this result was generalized by L21 again with the standard contact structure by Riniewicz and myself. So we proved that if you are given a dynamically convex contact form on this length space here, then you have this special periodic orbit with index 3, the same as here. that it admits this periodic orbit, which is the boundary of a global surface of section. And then it was later generalized by Schneider for LP1, again with the standard contact structure. And then this conjecture is about the existence of these very special orbits for more general length spaces like LPQ, or I think the next step would be to understand this theorem in the case of LP P minus 1 with the standard contact structure. I mean, the standard contact structure is the one which comes from the trisphere for the usual action. Okay, so and in that case, in all these theorems, what you obtain is that the orbit has index 3, but in the general case, it seems that the orbit, this special binding orbit, could have index in a certain range, which may depend on P or Q on the length space. Okay, so in the case of L32, which is that case there, I think that the statement should be, the conjecture is, it has this special periodic orbit with index, the contractible one. When you iterate three times, it has index 3, 4, or 5. It depends on the compactness properties. So these theorems are proved like deforming a foliation from a setup that you understand very well to one case that you, for instance, one case that you know some property like being dynamically convex, and then you deform the foliation from one situation to the other, and something survives because we have the SFT compactness theorem, and then what survives under some good conditions like being dynamically convex, we see that the foliation can be pushed to the end to produce a foliation also here, and it's even possible to estimate the indices of these orbits, again, using all the powerful of the holomorphic curves. Okay? So this would be a conjecture which has a version for LPQ. And another result, which is not published yet, but I would like to mention, also with Rinievich, which is the following. Again, suppose that you have a dynamically convex contact form on the trisphere with the standard contact structure. Then what is known is that you have a Hopf link, this pair of periodic orbits forming a Hopf link. Each one of them is the boundary of a disk-like global surface of section, but more than that, you can even produce an annulus-like global surface of section associated to this link. Okay? The boundary is this link. Okay, and it's just a very simple situation. Again, this theorem it's much more general. It's more or less the philosophy is when you have a contact manifold, a Hebb flow, which has an open book adapted to the flow, and then it's a positive open book. And then you produce holomorphic curves. The leaves of this open book are holomorphic curves, projections of holomorphic curves, and then you deform your given situation where you understand very well to the situation that you are studying, again, using SFT compactness theorem and all these algebraic invariants that we can, the asymptotics, everything that we have available to produce in this other situation. In general, we can say dynamically convex, but we could give like even weaker conditions that allow us to push the foliation to this other situation and to produce a new open book. If the same orbits are given, I mean, suppose that the orbits are given, then you produce the open book adapted so that the binding is that given set of orbits. So in this case here, for instance, you can take any pair of these orbits here and they will form a Hopf link on the 3 sphere. Since it's dynamically convex, so each pair will bind an annulus-like global surface of section, which is not so clear how it would, we could see these new open books associated to these orbits.
So you're saying that if you take any Hopf link of great orbits,
Yeah,
then it's going to get them out here.
yeah, exactly. Yeah, any. And these guys are Hopf fibers. They are, yeah, you just have to be careful if those, for instance, the blue one going this way with the other one going the opposite way, they form a Hopf link. Okay. And I think you can take any combination. You just have to check that, yeah.
Does one always exist?
You mean where?
Is there always a Hopf link?
Yeah, dynamically convex, always you have a Hopf link. Yeah. So you have this index 3 orbit, and it's a boundary of a disk-like global surface of section. You have a fixed point of the first return map, and it forms a Hopf link. Any fixed point would form a Hopf link with the.
You said before that according to the energy is harmless. That's 7.8, and the other
Yeah. No. Depending on the. In beginning, it's elliptic, but when you are close to the critical level, it bifurcates and becomes hyperbolic. It's, in this picture, you see here. So the blue one, pi 7, pi 8, they are here. Okay, they are elliptic. But then, if you increase the energy, then they are in the middle here. And there is a bifurcation here. It's hyperbolic. They are in between these two circles that are period 2 elliptic orbit. Yeah, here so okay, let me say a little bit about what's happening above the critical value. So it's still possible to use a shooting argument to produce. So it's known, because it's a theorem of Lyapunov, that nearby, so that there is this rest point. So the critical level projects here, and then above it's like that. And it's known that nearby here there is an orbit which is hyperbolic. It's a theorem by Lyapunov. But for energies very close to the critical one. But it's possible to prove that for every energy above the critical value, you find this hyperbolic orbit here. It's like, something is wrong with this. Okay? So it's not a straight line. This is a real orbit. It makes something like that. It's difficult to find explicitly, but you know, numerically, it's possible to, it's very simple to estimate. And this is the hyperbolic orbit. And so if you take the projection of the energy level into that orbit that we see red there, it's like a two-sphere. Okay. Where in the equator is the orbit, this hyperbolic orbit. And one hemisphere corresponds to the orbits that are pointing, let's say, inside that yellow region. And the other, so here is going one direction, and the other is entering that region, here is exiting that region. And by symmetry is the same in the other three necks there. And then, so it's for every energy greater than the critical value, 1/6, you have this situation. Just one hyperbolic orbit connecting these two boundary components. Okay? And you have this picture there. So let me so this region here that projects in the yellow one. This is a different color. I don't know why it's projected in a yellow, but it should be a different color. But the yellow one, the yellow region, the projection of the energy level in this yellow region, you see here, should be a different color. Is what we see here in this region. And there are these two spheres separating that region there, okay? See this picture here. And we see in the equator, this orbit is like going around. These three hyperbolic orbits, they are called pi1, pi2, p1, p2, p3. And in this case, the dynamics is much more complicated because they escape. Some orbits do not escape this region here. And then, for instance, you could do, there are a lot of theorems about this symbolic dynamics in this region here. They are hyperbolic, so there is the branch of the stable and unstable manifold of this hyperbolic orbit. And it's also possible to prove that when you have an orbit which is crossing this red region here, like going up, crossing it will escape, okay, in the other direction. So it must escape. It's the same problem as before. And then, so what in this case it's expected to happen is the following. Because so this so the you can create many different types of symbolic dynamics. Like for instance, you have an orbit which is like coming from this region, and well, because you have a hyperbolic orbit, you can. Yeah. But yeah, maybe I can. So the picture that it's expected to be happening here is the following. So there is a fourth periodic orbit here inside this region here, that I don't know which one is, because these orbits, they survive for energy slightly above, but they might not be this one. So there must be an orbit here which is unknotted, which is very special. Like it's the boundary of a family of disks, which is foliating the energy level here. And you see here. So these are disks. This is a knotted periodic orbit here, this Q. This should have index 3. So maybe not one of these orbits here. It's another orbit that bifurcated. And so there is a family of disks, and this family of disks to this guy here, they break. And we see a cylinder here connecting this orbit to pi2, to pi1, to pi3. These are cylinders connecting this orbit to this one. And in the complement of these cylinders here, we see 3 one-parameter families of disks to this guy, foliating all the space. So this is what's expected. Because the reason it should hold, maybe this type of foliation could explain a lot of the dynamics observed in these levels. And so I said that, so in the beginning it's strictly convex, but then it reaches the critical level. It's not strictly convex anymore because there are points where you don't have positive curvature. But these points are, it's like just a line of points inside the energy level. It doesn't make too much difference. The dynamics here is still dynamically convex on the critical level, when you go slightly above, then you lose convexity for sure, because, you know, in this region here of the neck, it's not convex, of course. And so there is a small region here where we lose convexity. And even here, this region is not convex anymore, but still it's possible to control the linearized flow, so some properties remain. And so it's still expected that even if you lose a little bit of the convexity, you can still control the indices of the orbits in this region where you lose the convexity in such a way that you can produce this foliation. And the idea to produce this foliation so this is a work in progress by Nayara De Paulo, Alexander Schneider, and André van der Linde. And the idea to produce the foliation is the following. So so let me try to explain. So you lose convexity, but you have some control of the index around this region. So this is that region, this ball with these two balls inside removed. And then we can cap these three balls, like taking symmetric regions here, like changing the Hamiltonian in such a way that this becomes compact, deform the Hamiltonian in such a way that you cap this region here. And then for this adapted Hamiltonian, so the projection, it's still a kinetic plus potential Hamiltonian. So it's again a three-sphere, but with these neck regions here, okay? And in this region here, the index is very well controlled, because you can make it small and essentially convex here. So this would be the estimate, okay? Here, you have a good control on the index. And then there is a theorem by Hofer, Vysotsky, and Zehnder, which if you perturb a little bit the flow here, the Hebb flow, this is a flow on the tight three sphere. If you perturb the flow a little bit, then it has a foliation. Foliation with the index 1, 2, and 3. Only there. And it's possible to show that only here with index 2. This foliation by Hofer, Vysotsky, and Zehnder might have index 1 orbits, but then we can estimate that this does not exist in this situation here, only 2 and 3. And the ones with index 2 are only these Lyapunov orbits in the neck. Then you cap this region here. And then you apply this theorem for a perturbation with a special J, and then you take the limit, and you do the analysis to control the stuff. And then it's really a stable foliation in the sense that when it's applied to this type of system, the binding orbits of the perturbed, they converge in a very good way. They do not explode or they do not collapse to each other. They converge, they really converge to periodic orbits of the same properties in the limiting situation. And then the foliation, which is given by holomorphic curves, then you can also prove compactness properties for this foliation, then it converges to the limit to a foliation to the original system. This would be an approach. I'm not sure if this is going to work, but it seems that it works because the index can be very well estimated, even in this region where it's not convex. Okay? In this region, you lose a little bit, but there is something very interesting that even in some regions that it's not convex anymore, the linearized flow still rotates positively. So you can control index with action. And then this is sometimes enough to obtain compactness.
Sorry,
I don't know. This is a good question. I don't know. This has index 3. But my guess is, where is it? My guess, it has bifurcated from a hyperbolic, the one which was elliptic and becomes hyperbolic here. It has index 4, and I think that nearby there is an index 3 orbit, but I'm not sure. Yeah, I would like to know where this orbit Q is. It's not one of them because the indices of these other orbits, they tend to be very high. Well, pi 1, pi 2, pi 3 for sure it's not. Pi 4, 5, or 6, they are hyperbolic, and I think they have index 4, so it's not them. And the others, all, again, because of this bifurcation, I think that there must be some orbit with index 3 nearby here. So it's a very interesting question, where this orbit is. So it should have index 3, and there should be the binding of this foliation in this region here. Maybe numerically it's possible to catch it, but it's not one of those, I think. But I'm not completely sure, because it's everything numerical. I did everything, and nobody ever computed the indices of these orbits. At least I haven't found anything about the indices of these orbits. So maybe it seems to be something very, very important here, but nobody ever cared of. They only, oh, it's hyperbolic or elliptic. They don't matter if it's so. But, okay, and of course this could be proved slightly above the critical value. Probably it holds for every energy greater than 1/6. This would be like the final foliation for the flow, because then you would explain essentially everything, at least in what is possible to capture from this picture. But what is known is that the index 2 orbits, it's unique. This is in every region of the neck here, you have only one. So it really indicates that this foliation is somehow stable, because this orbit with index 2, it might degenerate and then bifurcate. And if it bifurcates, then you lose this foliation. You have to consider more complicated foliations, which take into account this bifurcation. But it seems that, no, these orbits are always there. They are unique. So something is stable when you increase energy. So it should be the same picture, I think. So this is a question. Okay, I think, yeah, this is work in progress. Not yet sure about this picture, but should be something like that. Okay, thank you.